Okay, so yeah, this is the class. So just to make sure that everyone like is on like the same page, um, how familiar are you guys with cross ratio and like homography and stuff in general? Okay.
I'm not too familiar.
Oh, it should be fine actually. So let's first define the space we're looking in. It's called CPN. This stands for complex projective line. So if you know like barycentric coordinates, this is basically like the same thing, except you it's complex space, and we define the points uh A, B. No, you don't need to know Barry, such that A, B. Wait, hold on a second. Okay, so you define it A, B such that A, B in the complex plane like this, and such that A colon B is equal to KA. Hold on a second. Okay, sorry. Um, yeah, KB like this. So it's like basically this is basically equivalent to scaling it down to A colon 1 and then just adding in the points at infinity such that like if B equals 0, example. So you can think of CP1 as basically just the complex plus 1 point at infinity. Does that kind of make sense? Okay, so anyways, CP2. This is called like the complex projective plane, and it's basically the same thing, but you define the ratios A colon B colon C such that, and you can't have A B C equals 0. You can't have this because this is just bad. So the structure of CV2 is basically like you can set C to equal 0, and then this space A colon B colon 0. This is basically just like a line, right? We call this the line at infinity. And the nice thing about CV2 is that like you don't have like undefined parts of lines anymore. So like if you have any two lines, they will always intersect at some point, even if it's at like infinity, if they're like parallel, right? So that's a nice thing with CV2, and we will elaborate on this some more. And now the real objects with what like doing in Geo is polynomials. We're looking at like the zero sets of some polynomials. Like for example, like a line is just the zero set of some polynomial, like ax plus by plus cz equals 0, such that, right? This will give a line, and like a conic, it would just be like something like this, and this would be uh this, right? It would be the zero set of this polynomial. Hopefully this kind of makes sense. And the thing is like, since we're looking at like some complex space, you can actually, oh yeah, Wait, no, it's not because remember it's homogenized anyways. So like because you this is equal to this. So the zero set of like any polynomial like in regular 2D space, like for like suppose you want to solve this, then this is the same thing as this. I mean, sorry. Okay, hold on. Yeah. So hopefully this kind of makes some sense. So we get to define any circle in complex coordinates as basically just this. I mean, sorry, this is times like p times that and q times that equals like this. And the nice thing about this is that no matter like which PQ value you choose, these points will always satisfy this equation by just like plugging it in. And so this implies that any circle in complex coordinates, it will always go through the 4 points. I mean, like it will always go through the 2 points, this and this. We call this I and J, and we call these the circle points because every circle goes through them. So like you can define like 4 points being concyclic as just like 4 points A, B, and C, D as just A, B, C, D, and these 2 points, 1, I, 0, and 1, negative I, 0, as these 6 points lie in one conic. And hopefully this kind of makes sense. So any conic going through these 2 points is just a circle. And these are complex, so you can't like see them, but just try to visualize them somehow. Okay, now it's some projective stuff. So you're gonna actually embed copies of CP1 in CP2 like this, basically. Like if you have a line, like CP2 is defined by two complex numbers plus like the line infinity, right? So it's actually two-dimensional. And CP1 is defined by one complex number. So like you might think of the complex plane as like two-dimensional, but it's really just one number, right? So it's actually one-dimensional. Yes. So this actually lets you view like lines and circles in the regular like plane as just copies of CP1 inside it, which is stupid. But like this lets you define like cross ratio and stuff if you know what that is. But this is not very relevant to today's class. Yeah, if you know what a Mobius transformation is, the transformation setting this line to this circle is this basically for some A, B, C, D. But this is like unnecessary, I think. This is the important part. If you have a degree 2 three-variable polynomial, so this is just a conic, right? Then how many coefficients does it have? Well, you just solve like, yeah, you just solve like this, right? Which is like equal to like something, but it has 6 solutions, right? Yeah. So it has 6 coefficients. And this means that up to like scaling, since it's like homogenized, like it's equal to 0, so you can just scale one of these to be 1. So we actually only have 5 degrees of freedom. And hopefully this makes sense because like if you have a conic, you can draw a conic to any 5 points, right? So yeah. And now let's look for cubics. So how many coefficients does one have? So like x plus y plus z equals 3. Well, this has 10 solutions, right? Yeah. Like for, yeah. So this implies that any 9 points would give you a conic. That's because it's because like 5 choose 2, right? Equals 10. Yeah. So this means 9 points to give you a cubic, which is useful. And a conic is 5 points. And why is this 3 and not 5? It's because it's really just the 3 points A, B, and C plus the 2 points 1, I, 0, and plus 1, negative I, 0, which is still 5 points. So a circle is just a conic through these 2 points. Yeah, that is the way we derived it. And now this one's important too. Yeah, it is, I think. Physics. So you know that in like the reals, like you can have like a line and a line like not intersect, or like a line and a circle. Like these do not intersect, right? This and this. But the nice thing about complex space is that complex projective space is that these two intersect at point infinity, and these two actually intersect at some like complex coordinate by like fundamental theorem of algebra, right? So, for example, if you have a degree 2 and like another degree 2 like this, so two conics, these will give you 4 points. And for like a circle, like this and this, you have these two plus the two circle points I and J equals this, yeah, you know. And this is useful. Pay attention to this. And here's the main theorem we'll use to deal with cubics for this session. So I claim that if you have two cubics that go through 8 points, so like if you have 8 points like this, oh, it's cubics. Cayley-Banana. So like if you have a cubic through these points, since you have a free degree of freedom, right? Because you could just like, oh, what the hell did I draw? Okay. So we said we have 9 points to give you a cubic in general. So this means you have like an extra degree of freedom. So you can do it like this, right? Crap. Like you can draw multiple cubics through these 8 points. What Cayley-Bacharach says is that there exists a ninth point at this point, like for example, such that every cubic through these 8 points also goes through it. And this is special. Like conics don't do this. Lines also don't do this. So this also means that like there's some configs of so like if you have 8 points in the plane, then there's a way to determine a ninth point such that like all cubics pass through it. And there's a really nice construction at this point, but it's kind of complicated. So the intuition behind this theorem is that, well, if you have two cubics, they would intersect at 9 points, right? Because 3 times 3 by Bezout's theorem from before, right? By this, since you have Mn. But you only also like you also only have 9 degrees of freedom in a cubic in general. So the number of intersections of a cubic is actually exactly equal to the intersections of the number of degrees of freedom. And this means that you kind of like lose a degree of freedom when you do this, which that's the intuition behind this, basically. So here's some examples of it. Prove that for a conic and 6 points on the conic, that if you intersect this, 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 and this, that these points will be on a line. So do you guys have any ideas? Remember, you can define a cubic as like either 3 lines, a line and a conic, or just a cubic. So do you guys have any ideas on this? Well, we're trying to prove that. Okay, so I'll give you a hint. One of the cubics that I use is actually this line. Is this line and yeah, you can do that. Sure, why not? This is one of the cubics you can use. That's one of the cubics. So find some more cubics in this diagram. Yeah, conic plus black line. Yeah, so you just do this. Like this guy and this, wait, is that right? No, that's not right. You do on this guy, and this guy. And then by Cayley-Bacharach theorem, these intersect in 1, 2, 3, 4, 5, 6, 7, who's the eighth? Oh, I see it. It's because these are double points, yeah. So that means by the theorem that a cubic going through um going through 1, 2, 3, 4, 5, 6, 7, 8, 9, going through these points, it will always go through the ninth point, basically. So if that doesn't make sense, I'll re-explain it. Sorry. Yeah. You want to pick these points. And what okay, the first cubic you pick is this, like this exact thing, which is 3 lines, so it's a cubic. The second one you pick is this. Yeah, it is. I'll show some examples of it later. So that you choose like these two like zigzags basically. Does that make sense? Oh yeah. Yeah. So and then finally you draw a cubic through 1, 2, 3, 4, 5, 6, 7, 8, and it'll always pass through this one. So that means G H I A E C D P B. These will all lie in one cubic, and since these lie in one conic, these had to be on a line. And here's some more examples of it. You might be familiar with like Reims theorem, like if you have like a line like this, and then you draw 2 parallel lines like this. Then there's like a theorem that says this guy and this guy are parallel, basically. Yeah, it's like badly drawn. That's called Reims theorem. There's a generalization for this. If you draw like a conic through these 2 points, then these also be parallel. And the proof of this is really nice with Cayley-Bacharach. So basically, you do on this guy and this line, and then you do it on this guy and this line. And these will give you the points like 1, 2, 3, 4, 5, 6, plus the point at infinity. this way, right? Because these two are parallel. And plus the two circle points I and J. Would these equal like, the 0, I mean, sorry, 1, I, 0, and, since these two are circles, right? So that means through these 1, 2, 3, 4, 5, 6, 7, 8, 9 points, there's going to be a conic and a line through, well, we know that these, like, what line goes through all of these points? It might not be obvious. Yeah, I claim there's one line through these 3 points. What are the line? Well, the 3 points, the point and infinity from these two lines, and I and J, which are these points. Yeah, the line you pick is really just the line in infinity. So like the line A colon B colon 0, which all of these 3 points lie on, and plus this conic. So since these, so by Cayley-Bacharach, we have that 1, 2, 3, 4, 5, 6, and 7, 8, 9. Since we have these lie in one conic, but since these lie in one line, these have to lie in one conic too. I mean, one cubic, sorry. Hopefully that makes sense. And now radical axis is really easy with this. Like radical axis theorem is like this, and this intersect at K. So to do this, you just do conic plus line like this, then conic plus line like this, then conic plus line like this. Yeah, but this is like funny, so we do that. It's by parallel point, yes. But these two cubics give you it instantly. So here's some more funny examples of this. You might know that for a quadrilateral, ADF, ABE, FEC, and DBC. Oh, okay. If you have 8 points, well, like some new people just like came into the room anyways, so like yeah. Then do all go to a ninth point? I mean, it's not that bad to remember. It's like kind of trivial. Okay, so Mikel point is basically like these go through a common point. We call this the Mikel point of of DFPE, and you should be able to prove this with Cayley-Bacharach. It's not bad. Yeah, it's really funny. So the main idea behind this is that there's a total of 4 cubics in this diagram, the yellow, red, blue, and green ones, right? So that means like let's take the red and green ones. Then you have the points 1, 2, 3, 4, 5, 6, 7, plus I and J. So keep track of these. So that means that let's take the yellow one basically. Then we know that it'll go through since A, F, E are collinear, then we have that D, M, B. Oh, I and J are the circle points, but yeah, these ones again. So we have that every circle passes through these points I and J basically, these points. So that means we have the D, M, B, C, I, J line one conic. since AFE, DB, MC lie in one cubic and AFE lie in one line, right? But any conic through I and J is just a circle. So that means D and BC are cyclic. And same for AMEB. And then we're done. And here's an actual contest application of this. This is really funny. Oh crap. Okay, so what's the key insight of this? Like the key insight is actually just uh realize that this is symmetric. Like it's nothing special about X and Y. You can do the same thing on like this guy and this guy. Let's call these not W, let's call like yeah. And do you guys see the solution now? So what does like the symmetry in this imply? Like how can we rephrase this? Like by symmetry, I mean like if you swap X, Y with M and N, then it still holds. How's it deep? Wait, why did you extend X, Y to A, B, C, D? I'll do this. That doesn't even help, I think. Okay, here's a hint. What do we know about line MN, like based on the problem statement? Like if this problem is true, then what do we know about line MN? Well, we actually have that. Like I claim that OP equals these points. Let's call these something like yeah. I mean it's XY, exactly. So let's call these W and wait, V, yeah. So then we have that OP, like if this holds, we also have that OP equals OW equals OQ equals OV, right? And what does this mean? Yeah, it means that we want to prove that PWQV is cyclic and that this is concentric with ABCD. So now do you guys see the Cayley-Bacharach? It's actually kind of special in this case. Yes. Yeah, if you guys have thought about the cubic thing before, suppose we can actually have a similar statement for degree 4 things, like a quotic. So how many times do two of these intersect in? 16, right? Equals 4 times 4 by Bazoots. And how many degrees of freedom do you have in this? Like how many coefficients? Yeah, it is. 11? How do you get 11? Yeah, 15. Because it's like, yeah, it's 15. Yeah. You want to solve this, which is just like 7 choose 2 equals 15. And minus 1 because homogenization. Oh crap, yeah, 6 choose 2. So yeah, it's 16 is greater than 14. So this means that for a quotic through any 14 points, oh, that's just stars and buzz. Yeah. So for a quotic through any 14 points, then it'll always go through 2 extra points. Does that kind of make sense? S- Well, okay, 1, 2, 3, 4, and then you put like this. Then you can like put these in 15 ways. Okay, yeah. So now we just use this extended Cayley-Bacharach on this. Yeah, the two green circles. So we do like, yeah, and 4 lines. So we do AD, M, X, union B, and Y, C. This is one of our quotics. And I think you choose, no, wait, do you choose the lines? No, I think you choose like, you choose AB, line AB, line CD, and like ABCD. Okay, now my question to you is find all 16 intersection points between these two. Yeah, what are all of the 16 intersection points of this? Just like put them in the chat if you see them. Oh crap. Q. Well, by Bazoots to 16. Yeah, A, B, C, D. Also P, yeah. W, V, X, Y. Yeah, okay. So, and what are the circle points? So, you actually have the circle points twice. Well, J, J are circle points. Because you have a circle, you have two circles intersecting. This is the union of, oh wait, sorry. This should be, that's a mistake. Yeah, yeah. This. So just like the red quotic and the green quotic. And note that the green quotic is two circles. So it will intersect the red quotic twice at I and twice at J. For circle points, I and J. So that means there is a quotic through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Wait, did I miss some? X, Y, P, Q, W, V. Oh, M, N. Yes. So now, here's the final trick. I claim that if you have two circles like this, concentric, these are concentric if and only if they are tangent at I and J. And the proof of this is just like solve this. I mean, y minus b squared. Just like yeah, just solve this with two different radii, and then you get that it's tangent to I and J, which is like stupid. And now you can just win. Like let's take A B C D, which will give you this one, this line, and then finally this circle. So it factors like this. That's a factor, and this is a factor, which is really funny. People solved it in contests like 15 million different ways. So like, yeah, probably someone did this. This is the intended solution. This is intended. Well, Rames is just Cayley-Bacharach, so like, Rames is a subcase of it. So like, I guess that still counts. Yeah, the CH is silent. Okay, so now it's starting to get to the cooks. Do you guys all know what an isogonal conjugate is? Like point P and P prime, such that these isogonal conjugates. It's fine if you don't. Yeah, it's really fine if you don't. So okay, so we call two lines isogonal if you have a triangle is like this thing. If these two angles are the same, right? These are called isogonal lines. Isogonal conjugates of points such that like I won't define it. These two are the same, and like these are isogonal. I will explain it soon. And these are isogonal. But it's like these two equal, these two are equal, and these two are equal, basically. And like an example of isogonal conjugates is H, which is the orthocenter of the three altitudes intersection point, like 90 degrees. We call this H. And O, which is the intersection point of the three bisectors like this. So, like for example, these two are actually isogonal conjugates, like this and this. And the proof of this is just because like this angle, wait, I'm gonna change this. This angle equals 90 minus this equals like you draw this circle and you get the like since H is a reflection of this over this, you can actually just like chase this to this. I think, yeah. And since this is 90 degrees, you want to prove that this is the same as like this angle, which is like trivial. It's like pretty easy. It's just angle chasing. Okay, so now the proof of degree 3, it involves a bit of Berry, which if you don't know, you can probably just skip, but the thing you need to do is if you know what Berry is, it sends you can't use convex. Isogonal conjugation sends point A, B, and C to oh wait, I'm gonna make it let's call it X, Y, Z. It goes to this is like well known. And this is the same thing as like because you can like homogenize it, right? Multiply by x by z. And note that like, do you know what degree is? Crap, I think I need to explain this. Uh,
Hey Alex, you're muted.
oh crap. Wait, how long was I muted for?
Like, yeah.
Okay. Okay, so now for yeah, that's the proof that it's a cubic because the line through it, it's connecting a point of degree 1 and a point of degree 2. So like you have to find a polynomial through a degree 2 polynomial and a degree 1 polynomial, and that's obviously of degree 3, basically. So it's a cubic. So like it will look something like this usually. Like if you pick a point P, it will look uh like this, basically. Yeah, they look kind of stupid sometimes, but like I can't even draw them, but they look something like this usually. Yeah, if you want to like look at these some more, there's like a whole like tool in GeoGebra to do them. They're important because they will always go through the incenter and the three excenters because oh yeah, and A, B, and C. They go through A, B, and C because like the isogot the isogot the isogonal conjugate of A is like undefined. So like by like calculus or something, that means it has to like if you like approach A from this point, this line would approach some fixed line basically. Yeah, it's like dumb. But they'll always go through A, B, C, I, B, and I, C, but these are the incenter and the three excenters, since these are their own isogonal conjugate, right? And similarly, they will always go through P and P is conjugate, all right, like this. And this is 9 points. So it has to be a cubic also. And it's determined completely by P. So here's a funny example of how to use these in contest. I think we have time to do this, right? It's like, oh, we have 30 minutes left. That's like bad. Uh, yeah, okay. I think we should be able to have time to do this. This is Lin poppable. Wait, I need to let some people in. Wait, actually, no, I don't think we have time to do this. Sorry. Yeah, we don't. We have to go through this stuff. Crap. Yeah. Okay, this is cool. This is like this cubic is the locus of points such that points P such that this is the same angle. It's called isoptic because it's like APD equals BPC. So it's like P sees these two segments with the same angle. It's a really dumb name, but like that's what people call it. The nice thing about this is that if you guys know what Wait, do you guys know like McHale point stuff at all? Like inversion? Okay, so if you invert at the McHale point, which is just this intersection, crap. Oh, it's already in my diagram. So there was an inversion phi at the McHale point such that like A goes to C, B goes to D, like F goes to E. E is like that point. And we call this Clausen-Schmidt conjugation. So after doing this inversion, any point on this, well, this angle is just going to become like these two being the same is going to be, well, A is going to go to C and B is going to go to D. So it's just going to be like the same thing. So the important thing is that under phi, let's call this cubic K. So 5K equals K. So this cubic is mapped to itself after the Clausen-Schmidt inversion, basically. And this probably lets us prove everything about this cubic. So like what are some example points that I will go through? Like what are some points such that yes, it is. Yeah, what are some points that have this? This should be, sorry, this is flipped. APD equals BPC. Just find all P that solve this. Like find like 9 examples. Because then we can draw the cubic. Is it obvious why like A, B, C, D line the cubic, or should I explain that? That's only if it's harmonic. They don't exist otherwise. Okay, so well A, B, C, D they line the cubic because this is a bit stupid, but it's like degenerate. And you can actually visualize this as drawing an ellipse with foci at B and D. Like let's say it's like this ellipse. Then I claim that these two tangents from A and from C, uh, these points will always be in the cubic, basically. And do you guys see why this is true? What should I explain? Well, we want to prove that this angle equals this angle, right? Like we want to prove that angle AL, I mean, just like let's put a point, let's call this point. So we want to prove that like DPA equals CPB. And to prove this, it's not that bad. All I just have to do is DPA. Well, note that P and D are just, I mean, B and D are two foci of this ellipse, right? So if you, surely you have seen this property for an ellipse. If you have two foci and a point on this, then this angles to the same. Do you guys know why this is true? Wait, like, do you guys know why, like, if you have two foci and an ellipse and a point on the ellipse, that these angles are the same angle? Okay, I'll assume you don't. Should I explain the proof? It's really simple. Yeah, it's tangent. It's really simple, and it's really nice. So we know that an ellipse is a locus of points such that P and Q, such that like points X, such that XP plus XQ is constant, right? So, and you guys have seen this problem before, like if you have P and Q, and you have a moving point X on this line, and you want to minimize this distance, right? And to minimize it, you just like reflect P over this, and you minimize this, right? And you like just draw the straight line. But so we know that for point X, we have that this angle equals this angle. I claim that this line is also tangent to some ellipse from P and Q. And we can prove this by literally just using this property. Like draw like the locus of constant this, and then the one we want to pick is just the locus such that it's tangent. And then we're done because these have the same angle. So that's cool. And then you use this to prove this directly by drawing this and this in, and noting that like, and you get that these two are the same by angle tracing, since like it's the dual of this with respect to the ellipse. Or just congruent triangles, but yeah. So this implies that if you draw like a degenerate ellipse with foci B and D, so just like a line like this, then these two tangents will also be on the cubic. But in this case, the tangent is clearly just B and D. So this proves that actually A, B, and C, D, if it's continuous, then A, B, C, D have to lie in the cubic also. So that's 4 points we have. Obviously, we also have F and E, since this angle is like constant and this angle is like 0, and like, so we also have E and F. So that's 5, 6. Do you guys see any other points? Like, what are some other points that also lie in the cubic? Well, the Mikkel point, obviously, right? Because you have, yeah, Mikkel point, you have this equals this by like inscribed angle property. So also have J, that's 7 points. Yeah, and you have the two circle points. The proof of that is complicated, but it's actually simple. It's because like the circle points, they will always be fixed by some inversion, right? Because they lie in every circle, and every point on a circle is fixed by the inversion. So that means that, and you know that this is just a locus of points such that like the inversion across the Mikkel point is equal to itself, right? But I and J obviously invert themselves, right? So that's easy. So that means we have 9 points, and that's enough. If you guys didn't find the circle points, the other points you can use is just the foot from I to this, like with this 90 degrees. And this comes up a bit in problems too. And also just like, wait, did I misdraw it? Yeah, it's just this point. Sorry. And also the closest split conjugate of J, which is going to be like L, basically. So there's a lot of points on this cubic. And here's the properties of it that we have. We already proved this by inversion, right? Um, this is complicated to prove. Do we have time? Oh, we do not have time. Crap. This we've proved by definition. And here is an important lemma that you should know. And I'll go through the proof of this really quick. It's pretty easy. Oh wait, do you guys see why this is true? It's because by the ellipse construction, you could actually also define it differently for by ellipses as just like inscribed ellipse and the locus of the foci of all of the inscribed ellipses inside this. Because also you have the same thing. Then the isogonal conjugate of any point P inside the ellipse is just going to be the other foci. Because you have this thing right before. You still have that like these angles are the same, right? By what we just proved. And same for this and this. So these are isogonal conjugates. So that's how we get this. And how we get this from that is because any point P, well, if like these angles are equal, oh, this should be like directed angle, sorry. So if you know what directed angles is, it just adds mod 180. But this is basically, yeah, this is like pretty easy. This is just by definition. Okay, here's some more examples of Cayley-Bacharach theorem. So I claim that in a cyclic quadrilateral ABCD, then if you extend this and this to meet at some points E and F, then you have McKell point. F is McKell point. And this is like well known, right? Okay, try to prove this with the theorem. Yeah, he is. Okay, Lin Pop probably. Yeah, try to think about this. It's like not that bad. I'll draw the cubic too if you want. It's gonna look like something like this. I said if it's cyclic. It's gonna look like this, I think. Yeah, that sounds right. Yeah, but the funny way is to use Cayley-Bacharach theorem. It's obviously just like Brocard's if you know polar and stuff. But this is also the way that you prove that the Newton line of it is um at the asymptote. Yes. It also goes to I and J. Yeah, here's a fact that I didn't bring up. I probably should. If you have a circular cubic through I and J, and you have a line, like, let this be its asymptote, and you have a line parallel to the asymptote like this, then if you draw like this and this, then this will always be cyclic. Like, draw any line through these points, this will always be a cyclic quadrilateral. And this is kind of insane if you think about it. Like, there's like a lot of freedom, but it's insane. Um, the proof of this is really simple. It's just Cayley-Bacharach theorem on the cubic K plus like these three lines. Sorry, this line, and the line in infinity. And then finally this line and this circle. So the proof of this is really easy. Well, the cubic K and the red cubic of, sorry, I'll give the points labels if yeah, the cubic A, B, C, D, E, F. So one of the cubics is just K, the other one is A, C, B, D, and the line infinity is this cubic. And the final cubic is just this. And the proof of this is because these intersect at A, B, C, D, E, F, I, J, since it's circular cubic, plus the point in infinity along this, right? So you also have the same thing for this, and then we're done. It's pretty easy because E, F, and this are collinear. So that means it has to be a cubic through A, B, C, D, I, J, which just has to be a circle. This is useful. Okay, now back to the problem. Okay, do you guys see what to use it on? So if you use Cayley-Bacharach on the isoptic cubic, so this one, let's call it K again, and then you use it on line EF union ABCD. Well, what are the 9 points that these intersect at? Well, you have A, B, C, D, E, F, M, I, and J, right? Because it's a circle. So then by Cayley-Bacharach theorem, there's going to be one cubic through all these points. So you can really just pick like this as a cubic and this line with this a circle because you also have that, you know that from like a previous slide that the foot from ABCD, like the foot from this point to this line, it also lies on K. So then just by like cyclic quads, like let's call this a phantom point, let's call it like M prime equals foot from X to EF, but that's X. Then you have like phantom points that, let's look at the cyclic quad B M M prime F and line DAE. And then since we have this 90 degrees, BMF is also 90 degrees, so we're done. That's pretty cool. And here's a big theorem that I was talking about for a while. It's called the Liang-Zelich theorem. This was like recently discovered in like 2018 or something like that by like two kids, which is they're genius. So this says that if you have a isopivotal cubic with pivot X on the Euler line, then and you pick any point. Actually, I'll do GeoGebra for this. Yes, it is. Hold on a second. Okay, I think it says visible. It should be, right? Yeah. This is really cool. Like, So let's pick a point P on this cubic. And I claim that let's reflect. Okay. What the heck? Like for this triangle, if you define the same cubic, like with like the same like corresponding pivot, basically. So IGH, let's call it also 2. Then F also lies in this cubic, as you can see. And similarly, this is true for a lot of triangles actually. This is just one of them. So there's this triangle. There's also the triangle if you do the lines to AF, BF, and CF, and you do like this, it's also true for this triangle, like this big one. Oh, what the heck? What the heck? It's true for this big one. It's also true for this is called the antipedal triangle of it. It's also true for the triangle you get if you draw lines AF, BF, CF, which is not very visible. Oh, the antipedal triangle. Yeah, yeah, it's just this and this. Pedal is like this. Do you draw the feet to the sides? Antipedal is that for like the opposite. You do this such that this is 90 degrees. This is take a triangle and like this. You draw these lines through it. Oh, what the heck? And then you draw the circle. And then you like take like this intersection point and you draw this, like the other intersection points of it, and like the triangle formed by the other intersection points, and the Carnot triangle of P, which is a triangle formed by the circumcenters of these three subtriangles. And this is like a really deep theorem, basically. Like it to prove this is like very, very, very long. They got it published and stuff. It's like deep. So here's a funny usage of it. If you don't know, the incentral triangle is a it's like take the incenter I and then draw these lines. We call these DEF. You can? How? People tried it. It's like bad to do with the complex because you can't find these points, and you also can't find this. It's like a lot harder than you think to do with the complex. I mean, these are like monstrous. Yeah, people tried that. Wait, do you guys all know what this is? You can do it with ChatGPT. How? I don't think ChatGPT knows what line OI is. Okay, and here's the solution. It's really cool. Oh, wait, it's not full screen. Oh, okay. So actually, I'll just do it on GeoGebra, so it makes sense. Crap, I have like no time left. Okay, so here's the problem. ABC. How can I fast forward this? I don't know. Wait, crap. So the main thing you gotta do is, do you see how to prove that this triangle and uh the antipedal of I, which is just this, like you guys know what these points are, right? These are the x-angles of it. So it should be pretty obvious that this is really just the antipedal triangle of I, right? So what this means is that let's construct O also. Okay, I don't think that does it. Let's call this O. So let's construct the antipedal of O also. Just like try to understand this, I guess. Because I have like no time, so it's kind of rushed. Wait, no, sorry. This should be in JKL. So construct the antipedal triangle of O inside side of JKL like this. Then uh we have that DEF and this triangle, the homothetic. Like you know what homosity is, right? Hopefully. Homosity is just like the sides all parallel and they're congruent, basically. Do you guys see why this is true? Okay, that's good. So so let the set of homosity of these triangles, let's call it, here it is. Let's call this point something. Let's call it like yeah, let's call it N. That's fine, let's call it L. So the first thing I want to prove is that L lies in IO. Why is this true? It's not trivial. Don't say it's trivial. Okay, so how do you do it then? Huh? Yeah, because I is just the antipedal of G, J, K. Wait, how does that doesn't prove it. Yeah. Actually, okay, you have to do a bit of a sublemma first. Um, okay, let's read anything to like something sensible. Let this be. Yeah, this is the last thing I'll do, sorry, because I'm like out of time. So now we have that we have that you could find the isogonal conjugate of O inside triangle RST. And if you guys are unfamiliar with like the Bevan point, then you can actually get that the isogonal conjugate of O is the reflection of the Bevan point of OST. Yeah, that's like, wait, this is like complicated. Okay, uh, so okay, if you know what the Bevan point is, well, it's pretty obvious that isogonal conjugate of O in this is going to be the reflection of O over the Bevan point, because the Bevan point of OST is just gonna be the ortho center of this basically. So yeah. So that gets us that the isogonal conjugate of O inside RST. Well, if you know what the Bevan point is, you know it will lie in line OI. So let's just draw this isogonal conjugate. It's gonna be like reflective outline. What is that? Oh my God. Yeah, this is probably like incomprehensible. Oh. Yeah, this point is the isogonal conjugate of O actually. Let's call this O prime. So you can redefine IO as line I O O prime. So now we just want to prove L lies in O O prime. So note that, do you guys know what orthologic triangles is? Like, um, you don't need it actually. I'll hide this. We have that, uh, where is it? I claim that this is perpendicular to KL. Now this sounds like wait, no, not KL. Sorry. EF. This is because triangles RST and triangles EDF, DF, the orthologic. And the thing about orthologic triangles is that like, so we call two triangles orthologic the if these intersect at one point. And the thing about these is that if this holds, then you also have that the other perpendicular bisectors of this, these also intersect at one point. So by this, we have that since the foot from F to this is simply FL. Wait, sorry. Yeah, it's since you have that. Did I screw up? Oh, I did. Crap. These are the orthologic ones. Like JKL and SRST. Since the perpendiculars to J at this, which is just like this line and this line and this line, they intersected O, right? So that means these are orthologic. So that means by this theorem that we have before, like uh this theorem, like we have that this, this, and these intersect at O prime, the isogonal conjugate of O. So actually O is just the orthocenter of RST, and O prime is just the circumcenter of RST. So then we have that by orthologic triangles, we have that this is 90 degrees, right? Like this angle is 90 degrees. And now since KL is perpendicular uh to this, right? Because it's the X center and the angle bisector. So then we have that these two are parallel. Like this line, these are parallel. because these are both 90 degrees. Does that all make sense? I don't know combo, sorry. So now that we have that these are parallel, what does that mean about the homothetic center? Well, it just means that if you scale it up from like, you can also do this symmetrically. So also that this and we also have that this line and oh wait, no, that's wrong. We also have that this line and this line are parallel by the same 90 degrees thing. And similarly, we also have that this line and oh wait, crap. This line and this line are parallel. So now we have the like since like the corresponding parts of the triangle are all parallel, that means they're like homothetic at a point on line OI, which is really good because I is the like these are corresponding parts of these triangles basically. So now we have that L lies in line OI, which is useful. And now here's the trick. Now here's the theorem. So let's erase all of these lines real quick. Oh crap, that's bad. Let's erase like we can erase O, I think. Yeah. Okay. I think that's good enough. Let's erase all this too. Now here's the application of the theorem. Let's look at the hold on a second. Let's look at the cubic with pivot as the 9-point center. Like if you remember what that means, it means that the locus of points such that P and P prime and the 9-point center are collinear with these isopivotal conjugates. And this is nice because we have that what's JKL? So rephrasing what we want to prove in terms of this cubic, we want to prove that O lies in this cubic of RST. We want to prove this. Like we want to, this is the cubic I was talking about. We want to prove that O lies on this cubic. And by Liang-Zelich theorem, this means that it's the same as proving O lies in this cubic of JKL, right? If you remember the theorem, it's just this. This is the theorem. So let's pick the pedal triangle this time. So that means we want to prove that O lies in the same cubic of JKL. But this also seems difficult, right? So let's do it again. And let's just do it on, yeah, we can do this on ABC next. But okay, and now it's easy. So by two applications of the theorem, we have that, let's delete this. We have that O lies on the cubic of RST if and only if O lies on the cubic of ABC. So how do we prove that O lies on the cubic of ABC? Like how do we prove that O prime, and N9 are collinear? This is easy, right? Well, what's O prime? It's just H. And why are these collinear? Well, it's the Euler line. Yeah, homosity at G. So I mean, not G. Yeah. So then we're done. So that means O lies in the cubic of ABC. So since JKL is the antipedal of that. I mean, respect to I. Then you have that it lies the same cubic of JKL, so it lies the same cubic of RST. So that means that O prime and N9 of RST are collinear, but we know that O prime is exactly just line OI. So then OI and N9 are collinear. And then we're done. This is a beautiful problem. It is clean. Okay, the other solution is like complex batch or something, according to that guy. Okay. That's like the end of the meeting. I have to go. Sorry. So see ya.